It is no longer as valid to assess a potential antihypertensive drug simply on the basis of its ability to control blood pressure. Today, the criteria for choosing the most appropriate antihypertensive agent must include an assessment of its intrinsic duration of action, as well as its performance in the management of side effects. Lercanidipine. Short plasma half-life. Long duration of action. In order to fully understand lercanidipine's mechanism of action, consider what happens after lercanidipine has been absorbed into the arterial circulation. Owing to its lipophilic nature, lercanidipine temporarily binds to red blood cells, lipoproteins, and other components in the plasma. However, lercanidipine's retention time in this plasma compartment is relatively short. Regarding its unique mechanism of action, a fascinating question thus emerges. How can we understand the long duration of action of lercanidipine in light of its short plasma half-life? Are there advantages to having an antihypertensive agent with these characteristics? The answers to these questions begins with understanding the properties of lercanidipine in the plasma compartment of the arterial network. Lercanidipine interacts with a variety of particles within the plasma compartment. Owing to its lipophilic nature, lercanidipine readily binds to lipoproteins. These particles act as vehicles to transport this lipophilic drug throughout the arterial network, where lercanidipine exerts its greatest effect. Lercanidipine has now reached the small arterioles. At the arterial wall surface, the plasma particles are moving quite slowly. Lercanidipine, which may or may not remain bound to these lipoprotein particles, can now passively transfer from these particles and penetrate into the arterial wall. This transfer process is facilitated by lercanidipine's high membrane solubility. Lercanidipine's high membrane solubility also enables it to easily transport across cellular layers of the arterial wall, making its way first through the outer endothelial cell layer and then into the underlying smooth muscle cells, its cellular target site of action. At the molecular level, lercanidipine moves into the plasma membrane of smooth muscle cells, where the calcium channels are located. Free to diffuse within this membrane compartment, lercanidipine can now bind to its target, the calcium channel receptor, blocking calcium ion movement into the interior of the smooth muscle cell. This blockade is the fundamental mechanism that results in relaxation of smooth muscle cells, which is manifested as an overall dilation of the arteriole. Vasodilation of the small arterioles results in a decrease in the resistance of blood flow throughout the arterial network, thus lowering blood pressure. Over a period of a few hours, lercanidipine leaves the plasma compartment and diffuses into cell membranes of the arterial wall. It is here, where lurcanidipine is retained until the next dose the following day. Thus, lurcanidipine's extended duration of action is due to its long retention time in the membrane buffer compartment of cells that make up the arterial wall. By quickly lowering the concentration of lurcanidipine in the plasma compartment, it is possible that associated vasodilator side effects may also be lowered. Lurcanidipine has the shortest known plasma half-life of the available intrinsic once-a-day calcium antagonists. This is the result of lurcanidipine's novel side chain chemical moiety that provides its high solubility in membranes and serves as an anchor to retain lurcanidipine at its target site of action. For the first time, we can begin to understand the molecular basis of lurcanidipine's unique clinical pharmacokinetics and excellent safety profile in the treatment of hypertension.